Okay, so welcome back. Today we are going to look at some of the techniques I tend to use when I am trying to figure out how to design a software solution to a problem. And in my case, generally it's a science engineering problem. And we're going to talk about some of the techniques I use to figure out how to write my software, how to structure my software. And I tend to use this especially on more complex problems, but also on what seem to be simpler problems, because in the real world, often it turns out that what you think on the surface is a fairly simple problem. When you get into it and you start writing down the code, you say, oh, wait a minute, there's an aspect to this I never thought about. And really, this is kind of complicated, so I need to step back and do a better design so I can figure out how to do this. We have an example series I did recently with a coding challenge, and we're going to use that as an example in this video to talk about a problem that on the surface seems pretty easy, but when you get into it, we definitely need to apply this approach we're going to talk about. Now, what we're not going to talk about is the latest fad of the day of the design principles like Agile and that kind of thing. To me, those are less relevant. It's more important to talk about specific problems that I need to solve and how I can structure a solution in the software world. So to start out, what you see here is the general approach I take when trying to solve either a big problem or a small problem. And that is, most problems tend to be in this format where you have some input data. You take that data, you manipulate it, and then you process that data, and the results of that data processing become your output. And this can be describing an entire problem or different modules or different components of that problem. And this makes things fairly simple where we have an input, we have some processing, and an output. And this is the approach I like to take because it's easy to understand and easy to implement. It's easy to debug. And when you come back in 6 months, if you look at things that are in this format, it's easy to understand what your code does and what the different methods and functions do if you put it in this format. So the input has different types of data sources like files or a database, or it might be data coming over a serial port or a network. And the part of the input is that you have to take that data, bring it in and parse it. And once you've got that data all parsed from whatever the input source is, you then send it to the data processing function, which has data structures. It does the processing, it does the logic that takes that data in a certain format and processes it as you want so that it's ready to output. And then the last phase is the output phase where you go to graphics, user interface, or you send it to files or to a database, or you send it over a serial port or network or whatever. But generally, this is the kind of structure that can define your overall problem or the different components. Now, when you look at this structure, what I generally tend to do is assume that the input and the output can be performed using reusable libraries. So I tend to develop my own reusable libraries to do the input data, grabbing the files or from a network, and then parsing it. And the same thing for the output, because usually it's fairly common where I'm doing graphics or UI, files database, and sending it over a communications medium. And as I mentioned before, I tend to generate my own reusable libraries. I don't like to rely on external Git libraries or open source libraries. I tend to trust my own work, and it's a little bit simpler and easier to understand. When it's wrapped up in somebody else's code, it can be often difficult to understand. So I tend to view the input and the output as something that's fairly simple that I can use reusable libraries. However, the actual data processing varies a lot by the problem that you're trying to solve. And usually this is the difficult part. And this is where I tend to apply the techniques that we're going to talk about in this video to deal with this data processing. So we need to find data structures, find out how to process the data, find out what logic we're going to use. And again, this can be the difficult part. Now, another thing I tend to consider is that the input data often needs a lot of error checking. So if I'm going to be doing data input, I know that if it's user input, there's going to be errors. Could be errors with network files or database files. So I tend to want to put a lot of error checking in the input phase. That doesn't mean that I don't have error checking here, but this is really, really important because you know there's going to be some bad data. Now, the example we're going to use is something we talked about in our coding challenge series, where we are taking this input data, which is pairs of numbers, and we are taking those numbers and somehow figuring out how to draw a diagram representing those numbers. And in the real world, those numbers represent the real world electrical power substations used by your power company. And each line of the pairs of numbers represents a line between those two substations or buses. So for example, I've got a line between bus 1 and bus 2, and you can see up here, here's bus 1, here's bus 2, and I've got a line between them. So the challenge was to take this data and somehow convert that into a diagram like this, representing all of the lines you see here and all of the buses. Now, as we said before, on the surface looks kind of simple, right? Well, when you get into it, this can get kind of complicated. So this is a nice example where we can show some of the techniques that we can use to break this down into components that are easily solvable. So the first thing I like to do is look at the data that's involved in the problem. As we said before, we've got buses, these blue lines, we've got lines, but there's other stuff we need to consider in order to do this diagram. So we've got, for example, data classes. We probably want to have a bus class. Again, this is a real-world piece of equipment. So other than just for this diagram, we're probably going to want to have a bus class to define this, because this problem is probably the front end to doing an engineering solution of this system you see in this diagram. So this is a great opportunity to define a real-world bus class and also a line class. So those are two classes we're probably going to want to use, but also we need to consider not only are these physical objects, but they also have on this diagram, they have properties like the location, the length of the bus, and the placement. So we're going to have to think about, okay, we've got bus and line classes, but we've also got graphical properties associated with those, even though they're real-world physical devices. Another one is a diagram grid array. So we've got this diagram, but we're going to have to actually put numbers to everything. We're going to say this bus 2 is going to be placed in a physical location in this diagram. So it's nice, as we talked about in the challenge, to define an actual array where we can place each element. And that means we probably want some class that is a diagram grid array that we can access and place things on the diagram. Now we're also going to need placement logic, and this is where the thing gets kind of complicated. We're going to need to say, okay, where do I place each bus on the diagram so that we don't have a confusing diagram and so on. So bus placement logic is something we're going to have a separate class to do the placement logic. And then finally, once we've got all this figured out, we've got all the buses placed and all the lines placed, we're going to need to have some sort of graphics function. We can have a class that actually draws the results on a bitmap or on a diagram. So these are the basic classes we're going to use, the basic functions and properties that we're going to use in this solution. So coming up with these data classes is a really nice way to start out, where you've got the data in components and now you can start to break it down into the different classes. Now, one thing we talked about before is in order to place the lines and buses on this diagram, we're going to have to define for the computer actual locations. We're going to have a grid of actual locations. And we talked about in the challenge where we would have, in orange, we've got these positions where we can put buses. And in blue, we've got these blocks where we can put the lines. So we're going to have to define this grid that has two arrays, one of these bus positions and one of line positions. So it's nice to define these ahead so that you can then figure out how you're going to do the placement logic. So the difficult part, once we've got a grid defined, the difficult part is going to be doing the placement. So for example, what we've got all of these lines and buses we have to place. What we talked about is taking one of the buses and placing it here on the left. And then once we've got that bus placed, we can look at all of the lines that come out from that bus and try to place the buses associated with those lines. So we've got a line from 1 to 5. So we're going to have to place a bus 1. So we can place it here, and now we have to somehow mark this position as occupied and this block as occupied. And we can do the same for all of the other buses. So the logic is going to be, how are we going to go through and figure out how to place each of the buses and each of the lines? So we've got one from 3 to 5, and we just place that. So we're going to have some logic to place that. So the challenge is, what algorithm are we going to use to make this happen? Now, keep in mind, there may not be a right answer to this. You may have to make decisions and trade-offs, as we're going to see with this particular problem. There are multiple ways that you can place these buses and it will all work. So you're going to have to define your own requirements. So if you're going to have trade-offs and decisions, you might also, in the process, consider making those as variables that you can modify later. So we'll keep that in mind as we go through the process. So one thing I like to do is figure out, okay, ultimately, what do I need in order for this to work? Also, what do I know? What is my input data? And then what are my constraints? What are my design constraints, and what are the constraints that I decide to add to this based on the trade-offs and the decisions I want to make? So these are 3 very important questions I ask myself in order to know how to design this. And at the end of the day, we're talking about computers, so we're going to have to put numbers to everything. So it's really important that you don't just put vague generalities. At some point, you're going to need to put those vague generalities down in numbers and variables and classes and objects and so on. So here's the stuff for this example. What do I need? Well, what it boils down to is, at the end of the day, I need to have bus and line lengths and positions in order to place them. So somehow from that input data, I'm going to have to get these values, all right? So we're putting numbers to these. We're going to have to know bus and line lengths and positions. Now, what do I know? What's my input? Well, whatever I can deduce from those pairs of numbers, that's what I know as input. And then what are my constraints? There's going to be some decisions I need to make on how to lay out this diagram so that it's easy to understand and everything works. So these are the things I need to first figure out. What do I need? What do I know? What are my constraints? Before I can go into the process of doing the design. So at the end of the day, we want to come up with a diagram that looks like this, and they're going to be buses placed in these positions and in these rows, and we're going to have to come up with an algorithm how to place this. Again, there's multiple ways you can do it, but we're going to have to decide how we want to approach it. So one thing I like to do, as you see here, is do a graphical representation of how I want this to be laid out. So here I've got this grid that defines our diagram, and basically I have positions, arrays of positions in orange. So I've got position 0, 0 here, position 0, 1, 0, 2, and then I've got these blocks where the lines go, and I've got block 0, 0, block 0, 1, 0, 2. So if you can lay these out, you can get a good idea of what actual arrays of data you can use to define where I put the lines and where I put the buses. And we know that we can now have arrays of rows and columns of positions and blocks. So again, it's nice to use this graphical view. This is a PowerPoint diagram. It's nice to have this graphical view of how we can lay everything out, because you can refer to that and not just think you know the answer when you don't. So let's think about, using this graphical PowerPoint, how we can place lines and buses. What algorithm we're going to use. As we talked about before, the first thing we want to do is arbitrarily select a bus and place that in the left-hand column, all of these positions. And then we want to place the first bus that has a line going to it from this bus number 5. So let's say we've got a line to bus 1 from 5, and we need to place bus 1. Well, as you can see, all of these positions are available to place bus number 1. But how do we go about figuring it out? Well, what we can do is for each position, occupied position for bus 5, we can step one column to the right and say, hey, is this available? And in this case, there's no bus here, so this is available. So we know we're going to have some properties defining for this position, is it available or is it not? Let's say we want to place the next bus. Let's say there's a line from this bus to another bus. We want to place it, but this other bus is a longer bus. How are we going to do it? Well, we're going to have to start from here, and we're going to go to the right and say, is this available? Also, is this available since it's a longer bus? So we're going to need some logic to go from here to the next column to the right and place the bus. But of course, we can also place it here or place it here. So we're going to have to make some decisions on where we want to place it if we have this bus 2 that we want to place. Now also, we could place it down this way instead of up. Again, that's our choice. Either way is fine. And again, we've got all these possible positions. So we're going to have to do some logic thinking about how we're going to define what's available for the bus and what is the length of the bus. Now we can also place it down here if we're willing to extend this bus, because all we want to do is draw the line from 1 to 2. So all of these are available too if we're willing to extend the bus. So we've got a nice graphical view that's pointing out that, hey, we're going to make some decisions about, are we going to extend buses and so on. So based on that, here is an English pseudocode of the steps we might need to take to place a bus. So we're going to start out by placing a chosen from bus on the left. That's our bus number 5. We're going to somehow choose a bus to start out. You got to start somewhere. And then we're going to get a list of lines from that from bus. What are all of the lines coming out of this bus? Once we've got that, we need, from that list of lines, get all the 2 buses that those lines are going to. And for each 2 bus, determine the lengths of that 2 bus, how many positions are required, and then for each from bus occupied position, step 1 position to the right and see if the required positions above and below are available, i.e. not occupied. So we're stepping 1 position to the right, seeing if that's occupied, and in this case we got to make sure this is not occupied, and since this is the 0th column, there's no position up here, so we need to determine, is this occupied and is this not occupied, so that we don't have a confusion and have one long bus. If it is available, place the bus. If it's not available, we have to go to the next from bus occupied position and do the same thing all over again. Now, once we've got that done, we need to take all of the 2 buses and make those from buses so that we can start with these. These are already placed. Now we need to go bus 1, what are all its 2 buses, and figure out how to place all its 2 buses. And then bus number 2, what's all its 2 buses? So we have to find the lines from these buses and then place the 2 buses. So this is kind of a general framework that I like to use, where I write some pseudocode. And these are in the format where you can fairly easy do some for statements, if statements, and stepping through the positions. So this is a nice way that I like to figure out what my logic, what my algorithm is going to be, so that I can convert that into code. Now this is just a framework. When you get down to it, there's going to be a little bit more complexity, but at least this is a nice way to start you out with some pseudocode that can be converted into real code. So at this point, we have some general techniques to apply to tackle our problem and convert it into software. In part 2, what we're going to do is go a little deeper and look at ways that we can extend those techniques so that we can design for code that's easy to debug, has good feedback, you know what's going on under the hood, good error checking and handling, easy to understand, and well documented for others and you in the future when you look at the code. Also, we need to consider future upgrades and modifications, And also we want to use generic components that can be used elsewhere. So if you like any of these videos, I encourage you to hit the like button, subscribe, hit the bell notifications, but most of all, please let others know that we're here so we get some views. Really appreciate it. Otherwise, take care. Have a really good day. Thanks.